So welcome friend, in today's lecture we are going to discuss about the physical principles of sensing. This is in continuation with my previous lecture. So today we are going to talk about the concept of capacitance. So we know that we have studied in previous lecture, we have seen what do you mean by electric charge, what do you mean by electric field, and how it happens, and what is the effect of that field and other points. So when we say that there are two parallel plates which holds the electric charge, it is called as a capacitor. So two parallel plates of metal. So here we can see we have already seen this type of concept. Now the only difference is that in previous case we have considered only this parameter. Okay, so this is the charge and this is the charge in the vicinity. This we called it as a test charge Q0. Now this is the one charge and this is another charge, and this charge has been provided with a battery, external battery, which is connected with a plus and minus. So this plate, let us consider this surface will have a charge Q plus and this surface will have a charge Q minus. So you can see that the lines or electric field which is going outward in this field, and here it is coming inside one. Okay, here it is coming inside one because it is Q minus, and the force on this one you are supposed to calculate. So this concept will form a concept for the capacitor. So you can see that if I'll consider a plate with a positive charge, that is this is Q plus, this is with all the positive charge over here and all the negative charge over here. So the electric field will move from positive to negative. Electric field will move from positive to negative, and the cross sectional area A, this is the cross sectional area A of this one, and this is the voltage V. So you can call this one as voltage V. This V is applied between these two fields, so I can say, or I can connect like this one. So this is a positive and this is a negative. So this is how you are connected, and these two plates are separated by a distance d. So this will form a capacitance, or this will form a capacitor. So capacitor may be characterized by a charge Q, the magnitude of charge on either conductor. So this will be plus Q and this will be minus Q, and it is applied by a potential V, that is the potential difference between these two plates, that will define a capacitance. So the ratio of charge to voltage is constant for each capacitor. The ratio of charge to voltage is constant for each capacitor. So I will say that Q by V, that is nothing but a capacitance. Q by V is nothing but a capacitance. So either I have taken the magnitude of Q. So Q by V, Q, that is the total charge divided by the potential difference, that will give you the capacitance of the capacitor. So we have already defined this. So C depends upon the medium in which the plates are immersed. So we have seen that the two plates, they are separated by distance d. So they are separated by distance d, and there may be a gap between these two, and they are immersed with this medium, and that medium so the value of C depends upon that medium also. That is what is the medium that is used or that carries the electric field between the two plates. So that also affects the capacitance C, and the SI unit of capacitance is given as a farad, and it is defined as 1 farad is equal to 1 coulomb, because obviously charge is in terms of coulomb per volt. So coulomb per volt will give you the farad as a SI unit for capacitance. and we know that we can define the capacitance in terms of microfarad, nanofarad or picofarad. So micro means 10 raised to minus 6, nano means 10 raised to minus 9, and 10 raised to minus 12, like that. So the capacitance is measured in terms of farad. So capacitance is very useful physical phenomena in a sensor that can be successfully applied to measure the distance, the area, volume, pressure, force. So these are the physical parameters. We can measure it very effectively with the help of capacitance concept. So I'll explain it later on how it is going to affect, because C depends upon the media, C depends upon the D, C depends upon the cross sectional area. So if the cross sectional area gets changed, obviously capacitance will change. So we are going to see this one. So a parallel plate capacitor which is having a plate area of area size A and distance between the two plates will be D, then you can get a capacitance C is equal to epsilon 0 into A by D. Epsilon 0 is the permittivity of that permittivity constant of this capacitance. So epsilon 0 into A by D, so that will give you the constant of that one. So I can say that epsilon 0 is the constant, so C is directly proportional to A by D. C is directly proportional to A by D. So if you are going to change the C as A, so let us consider that. Let me take the concept of this one. Let me take the concept of this one. Let us consider that this is the plate, this is the central rod, and to this rod there is a plate you are connecting like this, okay, and below that at a distance D you are connecting the other plate like this, okay. So this is the another plate, and when you move this shaft, when both the plates are opposite to each other, they are not overlapped at all, okay, they are not overlapped at all, so the capacitance will be totally different. But when you move this, so let us consider that you will be moving this like this, okay. So the second plate is moved like this, so this is what your cross sectional area, and distance is fixed, but the cross sectional area is now changed. Initially the cross sectional area between the two plates is overlapping of the two plates will be totally 0. Now it is 50% of that one, so the cross sectional area is changed, and because of that your capacitance will change. Now the dielectric constant, that depends upon what kind of dielectric you are using. So dielectric material, it may be air or any other dielectric material you will be using, and that dielectric material will increase the capacitance value. So that increase in capacitance due to dielectric presence is called as is because of molecular polarization. How the molecular polarization occurs, let us see. So here it is your plate, here it is your one plate, and here it is your another plate. So initially when the voltage is 0, when the voltage applied between the two plates will be 0, the dielectric material between these two plates, so dielectric material may be anything, so which is having insulator type of material, so this it is having its own dielectric material, and the atoms are not in a parallel plane, or they are not in a their orientation of their atom is in different direction. Now you can see the orientation of this one is in this direction, the orientation of this one is in this direction, but when you apply the voltage, what will happen? You can see here it is plus Q and here it is minus Q. That means you have applied the plus voltage over here and you applied the minus voltage over here. So So because of that, what happens, the orientation of these molecules will be like this. So the minus will get attracted towards the positive plate and plus will get attracted towards this one. So depending on its own orientation and the place, the force will be exhibited, and you can see that the orientation is in the field of in the direction of the field E. So you can see that the plus will get in the same direction, and minus will try to align themselves in a same direction. So the capacitance will increase because of that. So the dielectric presence will increase the capacitance. This is what the importance is, and you can define it. So if you are using a dielectric, then in that case you can define the capacitance C is equal to K into epsilon 0 A by D. Obviously epsilon 0 A by D will be the previous one, and K will be your constant you will be getting. So for a parallel plate you are getting the capacitance C is equal to K epsilon 0 A divided by D. So dielectric constant must be specified for test frequency and temperature. So you should know what kind of dielectric constant you are using. So if it is a air, then obviously the constant will be different. If it is any other insulating material which is used as a dielectric constant or as a dielectric, obviously the constant for particular that insulator will be totally different. So a good capacitor with dielectric constant K and geometry with A and D must be stable. That means even if the environment is changing, your capacitance should remain constant. So they should not vary with the temperature, humidity, pressure or any other environmental factor. That means your humidity, if humidity is there, if temperature is there, the dielectric material that you are using between the two plates, that should not change its property. The plate should not increase its length or dimension. The distance between the two plates should not be changed. So if it remains stable, then I can say that that capacitor is a good capacitor. Now the best example is that whenever you, the previous radios were there and you used to tune the frequency, there was a capacitor called as a gang capacitor, and that gang capacitor you used to tune it for a particular station, for a particular frequency, and for that purpose a multiple plates were there. So the concept was like this. So there was a tuning factor like this one, and these are the plates. So these are the plates like this, and these are tuned to a particular rod, and I used to change this in a rotational manner. So that used to change this cross sectional area, because distance used to remain same, but the overall capacitance, so we know that if you keep the capacitance in this way, so this is having capacitance C1, this is having capacitance C2, and if you put the capacitance in parallel, so total effective capacitance will be C is equal to C1 plus C2 plus C3 plus C4. So if the four capacitance will be there. So we have already studied these type of concepts, and the total effective capacitance, if C1 is changing, C2 is changing, overall capacitance will be changed because of the change in the direction of that rotation of the shaft. So that concept was used for such kind of capacitance measurement. Another concept are also there, we are going to see soon how it can be used for a level measurement also. So capacitive sensor is also a humiditive sensor. That means whatever may be the dielectric material you are using, that dielectric material, if it is sensitive for humidity, then you can use that capacitor for measuring the humidity also. So this is one of the example of this capacitance, how the capacitance can be used to measure the humidity. Now you can use the same capacitance for measuring the water level also, or the level of tank also. So you are using the two plates to measure the water concept. So it can be used for measuring the water. So you use the two plates and that plates are immersed in a water tank, and when the water level increases it fills up. So we have to take care that since the plates are conductive plates, so the short circuit should not happen, so the proper insulation will be taken care of, and that will form a capacitance. And when the level increases, so that level will change the total capacitance of this one. Now here you can see that. So initially when water is below this level, so the plates are above that level, so there is no any connectivity between that one, so that insulating coating will be there, that will be avoiding the short circuit because of water. Now as the tanks start filling up, so there is a water between the two plates, and that water will have a certain its own dielectric constant, and because of that the capacitance is going to change. And that capacitance you can calculate it as at a particular height h, it will give you the Ch is equal to C1 plus C2. When the height will change, the C1 and C2 will change, and obviously your Ch will also change. So that will be given by C0 into G1 plus epsilon into 0 into G1 plus epsilon 0 K into G2. So you can calculate C1 and C2. So G1 will be fixed, this K is going to change, and this is going to change the overall capacitance, and you can measure this capacitance change with the help of some electronic circuit or some other devices. So this change is directly proportional to the height of your level. So here you can get Ch is equal to 2 pi epsilon 0 ln b by a. So you can calculate this one. So h is known to you. So this overall height of the tank is known to you, where the capacitance will be maximum. This h is known to you. So this k is known to you. So you can easily calculate the value of Ch, and you can easily get the water level measurement with the help of capacitance. So this is how you can measure the capacitor, use the concept of capacitance for level measurement. So C0 is at initial level height 0. So this factor will be 0. This factor will be 0. This will be 0 in this case. So you can get this one, C0. So you can calculate the value accordingly. Now the next concept, this is how we have done with the capacitance. Now the next concept, and it is an important concept, that is called as a magnetism. So you know the magnet, so it is just like an electric charge. The only difference is that it has a material, a ferromagnetic material, which exhibits the permanent capacity of generating the field. So there is a strong similarity between the electricity and magnetism. So you can see that the two electrical charge rods have a like and unlike ends. Similarly, the two magnets have the two opposite ends. One we call it as a south pole, and another we call it as a north pole. So you have studied it in your school days, as well as in your college also, as well as you might have experienced it in your childhood also. You might have played with a magnet, and you might have played such kind of concept. You used to put a burr of iron on a paper, and you used to put it on a paper, and you used to put a magnet below that paper, and you used to move that, and accordingly that burr used to move on a paper. So this is what the game you might have done, or with the help of nails you might have tried to play it with this magnet concept. So this is the magnetism concept, and that we can use it. But before that, how the flux and everything or magnetic field affects the charge and how it affects the electricity, or how it can generate the EMF, that we are going to see it. So the magnetic poles always comes in a pair. So you cannot say, okay, this is only a south pole and this is only a north pole. Sorry. So whenever you take a magnetic bar, so let us consider that whenever you take such kind of magnetic bar and you say that if it is an S pole, obviously the other pole or other end will be the north pole. So it always comes in south and north pole, or it always comes in pair. So you cannot directly come, the whole bar is of south pole. Sorry, the other end of that bar will be a north pole. So magnetism is associated with the atoms and its arrangements. So as we said that it is a ferromagnetic material, and in previous case in capacitance we have seen that when we applied the electric field, the dielectric atoms they will try to align themselves in a particular direction. But in magnetism, all the atoms are aligned in a particular direction only, and that alignment makes the property of that material, and they are aligned permanently. That's why it shows the magnetic effect, and that has come from the material called as a magnum, and from that, that's why it is called as a magnetism effect. And you can go through the books and you can search about a lot about magnetism, because there are stones which shows this property in which all the atoms of that substance are aligned in a particular way. That's why they exhibit the south pole and north pole, and they shows the magnetism effect. So you can go through the internet and you can search about the magnetism in more detail. So we can see that if you place the magnetism pole in a certain space, that space pole appear or the space around that pole will be altered, and we call that altered space as a magnetic field. That means if you are putting this one and if you put a magnet in a space, so you can feel the effect of that one. Now if you put the magnetic field near to any small substance which is just like a small nail, and if you put a magnet over there, so the best example I'll try to give you the example of Tom and Jerry. So they used to play with the magnet, and if you have seen that serial, you can see that it used to attract the Jerry. Tom tried to attract Jerry with the help of magnet. So such kind of concepts were there. So it shows the magnetic effect, even though that was a cartoon, but you can actually experience it in your work also. So you can put a magnet near to nail, and you can see that nail which was initially at a stable position, and if you put a strong magnet near to that nail, so because of that magnetic effect of that magnet, the magnetic field, there will be a change in the stability of that nail, and that nail gets attracted towards the magnet. So that alter space, we'll call it as a magnetic field. So if the magnetic body is a small bar magnet, or it is a magnetic needle, and we'll try to find out in a particular direction. So because of Earth's magnet, we know that there is a south pole and north pole in earth, and it shows a gravity force, and if you put a needle, magnetic needle, then magnetic compass, it will always show you the north and south pole. So the north pole will get attracted towards south, and the south will get attracted towards north, and it will give you the direction of north and south. Okay, so this is how exactly you'll be getting, and the same concept is used in magnetic compass. So you can see that always the field will start with a north and it will end at a south. So the field will be like this, in this direction. So the field will be in this direction, and if you put a small magnet in this direction, then it will start exhibiting the force from this end, and the south pole will try to attract the north pole towards south, and the south will get attracted towards north. That means if the second magnetic field will be there, so the same concept we have seen in case of electric charge also, but now here it is having a dipole. Here it is having a dipole, one is the south and one is the north. So the south will get attracted towards north, and the north pole of this magnet will get attracted towards the south, and this south will get attracted towards north. So this is how the magnetic effect will occur, and the force F will be exhibited on that one. So the stationary electric charge have no effect on magnetic compass, and when we pass, so if you pass the current, so we have already studied that if you pass the current through an inductor, and if you put a compass over there, it will try to change its direction. It will try to change its direction because of the magnetic field that has been generated by this coil, that has been generated by the coil. So this is what the effect we are supposed to study. So if you pass the current, it will try to generate a magnetic field, and that magnetic field will try to change the direction of this needle. Okay, so and if you change the direction, of current, now the current is in this direction, so initially the needle will be like this, now north south. Now if you pass the current, and because of that the direction will be this one, and if you change the correct direction, or again it will change, the north will come over here and the south will come over here. So again the needle will change the direction. So this effect is there. Now you can see with this diagram, when you pass the current and electric field will be there, and if you try to put another coil in that one, so because of the magnetic effect of the coil that has generated this magnetic effect, because of that there is a deflection, and that type of concept is used in many concepts. It may be used for a induction purpose, it may be used for any other applications. The transformer is the best application of that one. So where current is used to generate the magnetic field, and that magnetic field is used to generate induction in another field, so that we are going to discuss it afterwards. So this magnetism will tell you the concept of that one, and this is associated with the solenoid concept. So the fundamental property of magnetism is that the moving electric charge, that is a current, essentially produce a magnetic field. Okay, the magnetic field you can generate it either by using the ferromagnetic material directly and passing the current, and the magnet will get that ferromagnetic material will get magnetized, or you can use a simple coil and you can pass a current and you can produce a magnetic field. So this is how you can get a magnetic field. Now you pass a current through a wire and magnetic field will be generated. So Faraday's laws of electromagnetic induction, that will give you the such kind of concepts. Now you can see that, and if you put a charge in an electric magnetic force, if you put a charge in an magnetic field, then it will exhibit a force and they will try to came into one direction only. Okay, they will try to come into one direction only. That means if I pass a current, that will generate a magnetic field, and if I try to put a charge into magnetic field, it will exhibit a force or it will generate a current. And that is vice versa. That means a magnet can generate electric force or electric parameter also, and electric current will also generate a magnetic field. So that is the important property of this magnetism, and that can be used for sensing applications. So electron continually spin, it provides a eddy motion around the atom, and electron movement continues to be in circular electric current in atomic nucleus, and this current will cause a small magnetic field. Or you do it in a reverse way, you put that charge, having certain charge, into a magnetic field that will exhibit a direction to that charge. So that charge will move further again. And the same type of concepts are used in ammeters and voltmeters and galvanometers. The previous galvanometers, nowadays digital concepts were used. The previously the meters used to have a permanent magnet like this, and you might have studied such kind of concepts in your electrical, and in between that I used to have a coil which carries a current. So a magnetic field was there, and when I pass a current through this coil, current I. So depending on that, the flux is fixed, this magnetic field is fixed, and I am passing the current through this coil. So because of passing the current through this coil will experience a force in a particular direction depending on the current. Okay, how much current you are placing in that one, and that current and that deflection of that coil is proportional to the current. So that concept was used in various meters used to measure the voltage and current. So this magnetism concepts were also used to measure the voltage and currents in ammeters and voltmeters. So if you are able to see such kind of concepts in laboratories, you can see these concepts. You can see the analog voltmeter or ammeters or galvanometers. You can measure the concepts of this one. Nowadays you are directly using the multimeters, that's why you are not able to see such kind of concepts, but the magnetic effect will play a very important role in this one. So atomic magnets may be kept aligned position in some material which have appropriate chemical composition and a crystalline structure. So I called that material as a ferromagnetic material, and various materials that you use that as a magnet, as a permanent magnet, they are the ferromagnetic materials. So one important concept that is associated with magnetism, the Faraday, he experimented some experiments on the material and came up with its own law. It says that if the electric charge is moved across the magnetic field, a deflecting force, I have already explained you, the two magnets, S and N pole, and a coil, I'll place it in between that and I pass a current. So this is the electric charge is moved. Electric charge is moved means this is moving electric charge is nothing but a current. Moving electric charge is nothing but current. Okay, so if it is moved, it exhibits a deflecting force. It exhibits a deflecting force, and that we have already seen in a previous diagram also. So this is the base of the fundamental electromagnetic theory. This is the fundamental electromagnetic theory, and Faraday has come up with this electromagnetic law. So deflecting electric charge results in electric field generation, and because if it is deflecting, so if you put it into that and if you pass the current, it will generate a voltage difference between the material and you can produce the electric current accordingly. Or if I put a coil in that, and take the previous concept itself, this is a magnet, and so let us say this is S and this is N. So this is N, and obviously the field will be like this. So there will be a field, and if I put a coil in this and if I start rotating this coil, so instead of this one you put it, and if I start rotating this coil, so what happens, that coil cuts the magnetic field, and because of cutting of that magnetic field, the EMF get induced, because the force will be exhibited on this coil and electrons, and electric current will be exhibited. And this is the concept used in most of the generations, most of the electricity generation, or you can generate the EMF by simply rotating it. So this is the best example of previous dynamometers or dynamo that you used to have to your cycles. So there was one magnetic material was there, and that material which is having a one rotating shaft, and that shaft was used to connect to your tires, and which is in contact with the tires, and as your cycle moves, that dynamo shaft will used to move, and because of that electricity was generated, and in a night the cycle used to have a headlight, like that concept were there. Nowadays nobody is using, so you can use such type of concepts also for generating the electricity. So I came across one kind of concepts related to this one also. One of my friend, he came up with the concept, he used this dynamometer concept, and he used one part of this coil to his foot and another part to his knee, and whenever he used to walk, he converted the longitudinal motion into horizontal motion into rotational motion, and that used to convert this walking style into electric voltage, and that he used to charge the his mobile. So that was the concept he used for making the concept, and this is what the concept of Faraday's law. You can use it in many concepts. So either you move, either you pass the current, that will show the deflection, or you show the deflection, or you move the give the displacement, it will generate the current, vice versa. That means if you want to measure the displacement, it will give you the proportionate current, and if you pass the current, it will give you the deflection. So if you want to measure the displacement, you can simply displace it, rotational displacement, you convert it into rotational displacement, and that rotational displacement will give you the direct current, and that current will be proportional to a displacement. So this is what the concept you can use for the magnetism. So the number of lines per cross sectional area, per unit cross sectional area, we'll call it as a magnitude of B, and we'll call it as a flux most of the time. So we'll call it as a flux. So flux of the magnetic field, it can be defined as phi of B is equal to integration of magnetic field over the area, over the unit area, and we'll call it as a flux. So this force FB is proportional to the charge, velocity and magnetic field, and we can define it. So here you put a charge in the magnetic field, here you put a magnetic field B and here you apply the force V, then voltage V, then here you can get a magnetic force that is exhibited because of B and V, and you can get it in terms of equation. The deflecting force FB is equal to Q0 into V and B. So, or you can simply say that FB is equal to Q0 VB into sine phi. So, phi is the direction between, or the phase difference between magnetic field and electric field. So, the SI unit of magnetism B is Tesla. SI unit of magnetism is Tesla and it is denoted by T, capital T. What is by T? 1 T is equal to 1 Newton per ampere meter. 1 Tesla is equal to 1 Newton per ampere meter. 1 Newton, so you are talking about force and you are taking the current and displacement. So 1 Newton per ampere meter, that will give you the 1 Tesla. And other unit is also there. You can measure it 1 Tesla into 10 raised to 4 Gauss. So you can measure it into Gauss also. So many of the manufacturers are using the Gauss, as well as they are using also Tesla type of unit also. So this SI unit of magnetic flux, if it is measured with the area, then it is named as a Weber. Okay, so if you are using the magnetic field, its unit is Tesla, and if you are using the magnetic flux, its unit is Weber, and 1 Weber is equal to 1 Tesla meter square. 1 Weber is equal to 1 Tesla meter square. So there is a practical device called as a magnetic field, which uses the magnetic field or which produces the magnetic field. It's called as a solenoid. So this kind of solenoid are used in most of the contactors. So you might see a relay type of concept, but that is not exactly relay, but here only a single coil is used. In relay, a single coil is not used. The principle of magnetism or induction is used in relay, but here a coil is used and which is generating a magnetic field, and because of that magnetic field there is a attraction and repulsion of the rod. So you can see that solenoid over here. So here you can see that this is the coil through which you are passing the current. You are passing the current and that will generate a magnetic field around this coil. And if you put a bar between this coil, so this bar will exhibit a force of attraction or force of repulsion depending on the force exhibited by the magnetic field. And because of that you can see when you pass a current, I'll show you with the example of this one. So here it is, sorry. So when you pass the current into this one, so what will happen when you pass the current, because of that this rod, the other rod end is connected to the spring, and when you pass the current, this rod, which is a metal type of plunge, that will get attracted towards this side and it gets engaged. It gets engaged with the coil, and as soon as you make the current off, it will be disengaged and it will move to, because of this spring action, it will move to its original position. Because of the spring action, it will move to the original position, and this is called as a solenoid. So I'm sorry, I'm not able to show it here. So the permanent magnets are very useful components for fabricating the magnetic sensors. As I said, the permanent magnets are very useful because when the coil came into its vicinity, or when the coil comes in the magnetic field, so because of that magnetic field, the coil cuts the magnetic field and that will generate the EMF, and